make a mistake in a question, well, let me know. All right, so chemistry 1401. This is kind of where we left off last chapter, or last class rather. We were talking about standard free energy of formation, and these are values that you can look up in the appendix of our class's textbook. So you can go into appendix G, I think it is, and you can look up all the standard free energies of formation of all kinds of different compounds. And we said that those standard free energies of formation are for a compound. If you have 1 mole of the substance, or sorry, it's the free energy change for the formation of 1 mole of a substance from its elements in their standard state, which would be 1 bar or 1 atmosphere and 298 Kelvin. So if it's forming, from its elements, then it kind of stands to reason that the elements are going to have standard free energies of formation of 0. So if you go into that appendix, you'll see that anything that is a pure element is going to have a standard free energy of formation of 0 kilojoules per mole. And again, you can look that up in appendix G, I believe it is. So with that in mind, let's take a look at the formula. Let's take a look at the formula for calculating the delta G of a reaction. And let's say we have a reaction like this one here. We went over this formula last class, and we said it's very similar to the reaction, or the formula rather, that we use to calculate the enthalpy change of a reaction back in the thermochemistry chapter of chemistry 1401 of general chemistry 1. So we take the sum of the the standard free energy of formations of the products multiplied by their stoichiometric coefficients, subtract the sum of the standard free energies of formation of the reactants multiplied by their stoichiometric coefficients. Okay? And notice that this equation only works when calculating the standard free energy change of a reaction at 298 degrees Kelvin, because we know that delta G depends on temperature, doesn't it, right? Delta G is equal to delta H minus T delta S. And so that tells us that if our temperature is not 298 Kelvin, that we're going to have to evaluate that free energy change if it's at a different temperature. Now, again, the most stable form, standard conditions, the delta G of formation of any element at its most stable form is defined as 0. And the standard states for gas would be 1 atmosphere or 1 bar of pressure, solids and liquids in their pure form. A solution is a 1 molar concentration. And again, if you have a pure element in its most stable allotropic form, it's going to have a delta G of formation of 0 kilojoules per mole. Well, with all that in mind, let's take a look at problem 7. We answered question 6 in the last class. It just simply asked, does delta G depend on pressure? And the answer is, yeah, absolutely it does, because delta S depends on pressure. In fact, we talked about that. We said if we increase the pressure on the gas, that leaves less microstates, or it decreases the number of microstates available to those gas particles, and so their entropy decreases, and therefore we drew the conclusion that entropy is dependent on pressure. And so, yeah, delta G is going to depend on pressure. Well, that takes us to question number 7. It says here, for this reaction, this is the combustion of methane. So if you take methane and you combine it with oxygen, you need 2 moles of oxygen for every 1 mole of methane. You produce carbon dioxide and 2 moles of water. So there's our reaction, combustion of methane. So if you've washed your hands today with warm water, well, you probably burned some methane in the process, because hot water in Colorado is usually produced from heating natural gas. Anyhow, it says, using the data that's shown below, calculate the delta G of this reaction, so the change in free energy of this reaction at 298 Kelvin. All right, well, if we want to do that, we're going to use the formula that we had on the last slide, okay, or a couple slides ago, which is this formula right here that I have in the yellow box. So what are we going to do? We're going to say that our change in free energy for our reaction is going to be the sum of the stoichiometric coefficients multiplied by the delta G's of formation of the products minus the sum of the stoichiometric coefficients multiplied by the change in free energy for the formation of the reactants, right? That's the formula that we need. You need to know that formula in this class. So let's see. Our products are carbon dioxide and water. So I have my carbon dioxide. I only have 1 mole of carbon dioxide, so it's negative 394.4 kilojoules per mole. I have 2 moles of water, so that's, I'm going to add 2 times negative 237.2 kilojoules per mole. I'll put all of that together, and then I'm going to subtract. Now, oxygen, keep in mind, has a delta G of formation of 0, right, because it's in a standard state. But for my methane, it has a delta G of formation, which is negative 50.8. And again, all of that, here, why don't I just sandwich it all in here, is kilojoules per mole. And so when you evaluate that, you end up with a delta G for your reaction as being negative 868.8, subtract 50.8 kilojoules per mole, and that gives you a standard free energy change for this reaction at 298 Kelvin as being negative, I should say subtract negative 50.8, which gives you negative 818.0 kilojoules per mole. There we go. So our delta G is negative, and so this is a spontaneous process, right? You know that when you take methane gas or any kind of hydrocarbon, octane, hexane, whatever, and you hit it with a spark, right? And if it's in the presence of oxygen, it's going to burn, right? Again, this is just the combustion of methane, and methane is CH4. All right, there we go. Next, it asks us to calculate the delta G at 500 Kelvin. Now, 500 Kelvin is not the standard state, is it? Right? Because if you look at our appendix, you're going to find the standard free energy of formation of compounds at 298 Kelvin. We've discussed that, but hold on. We know that if we want to calculate the delta G at 500 Kelvin, right, for part B, we have our delta G for our reaction is going to be equal to the delta H, okay, minus T delta S. Well, what I told you is that you can assume that delta S naught and delta H naught are constant with temperature. So even though we're going up to a temperature of 500 Kelvin, we can use the delta H and the delta S values that we get that's shown here, even though they are provided for 298 Kelvin. Is there going to be a change in the S values with an increase in temperature? Yeah, but only slightly. And so it's going to give us a good delta G value, which will enable us to predict whether the reaction is spontaneous or not. All right, so all we're going to do then is we're going to evaluate delta H, we're going to evaluate delta S, and then we're going to plug in 500 Kelvin. So let's start by evaluating delta H, and we've already gone over how to calculate delta H in the thermochemistry chapter. That's a formula, again, that's similar to the formula for calculating delta G. We take the sum of the stoichiometric coefficients multiplied by the heat of formation of the products, subtract the sum of the stoichiometric coefficients multiplied by the heat of formation of the reactant. So let's do that. I'm not going to write down the equation. I'm just going to start plugging in some numbers here. So for my products, I have my carbon dioxide, which is negative 393.5 kilojoules per mole, plus I've got 2 times negative 285.8 kilojoules per mole. So I've got all that, and then I'm going to subtract the heat of formation of my methane, which is negative 74.5, and all of that is kilojoules per mole. So I already went ahead and did all the math on that, and you end up with your delta H of your reaction as being negative 890.6 kilojoules per mole. So there we go. Now we've got our delta H. That is done. Now we need to evaluate delta S. Same thing. The delta S of our reaction is solved in a similar manner. We have all of our entropy values here. Notice that the entropy value for oxygen is not 0, right? You can only have an entropy of 0 when you have a perfect crystal, right, at 0 Kelvin. And so you're not going to find any element having a standard entropy of 0. So we're going to plug in our numbers here. We get, what do we get here? We get 213.6 plus 2 times the entropy of my water, which is 69.9. There we go. Then we're going to subtract the entropy of the reactants. So we have 186.2 plus, what is it? 205. Okay, so 205.5. So plus 2 times 205.5. So we'll put that in here. And then all of that is in kilojoules per mole. Sorry, it's not. Leon's getting ahead of himself. So we have joules per mole Kelvin. Make sure to pay attention to these units, unlike I just did. Well, actually, I was thinking about something else. But anyhow, there we go. So pay attention to the units, and we get that the delta S of the reaction. Get that our delta S for our reaction is equal to negative 243.8 joules per mole Kelvin. Or if we want to convert this to kilojoules per mole Kelvin, right? We know that in 1 kilojoule, there are 1,000 joules. So all I have to do is divide this by 1,000, and I get the answer in kilojoules per mole Kelvin. So I'm going to do that just to have it. I have divided by 1,000, and I get negative 0.2438 kilojoules per mole Kelvin. There we go. So now we've got delta H and delta S both, right? Again, we learned how to calculate delta H in General Chemistry 1. We've gone over it again here. We've learned how to calculate delta S. We talked about that the last lecture. So now that we've got our delta S value and we've got our delta H value, we know what our new temperature is. It's 500 Kelvin. Now we can start plugging in some numbers. So I'm going to write it out like this. I'm going to say that my delta G naught for this reaction at 500 Kelvin is going to be equal to delta H minus T delta S, which is negative 890.6 kilojoules per mole, subtract 500 Kelvin multiplied by negative 0.2438 kilojoules per mole Kelvin. Notice that the units cancel. And so when I simplify that, I end up with my delta G for my reaction at 500 Kelvin is being equal to negative 769 kilojoules per mole, like that. All right. And so at 298, I had my delta G as being negative 818 kilojoules per mole. And then when I jack up the temperature, you see that I get negative 769 kilojoules per mole, like that. All right. Well, with that in mind, let's move on and try questioning. Any questions about question number 7 before we move on to another question? Question 7 is a very common question for exams and quizzes and final exams in thermodynamics. Okay, it's just basically testing our students in making sure that they understand that delta S and delta H are not going to depend on temperature. Okay, making sure that they understand that you can use these values and you can still calculate the delta G with a temperature change. Okay, that's really all that question is about. But again, it's a very common question in General Chemistry 2. All right, well, if there's no questions about it, let's move on and try question number 8. It's in a similar vein. It says, use the information that's given here to calculate for the vaporization of liquid carbon disulfide, the standard enthalpy change. So we'll kind of break these up. So we'll call this A, the standard enthalpy change, B, the standard entropy change, and C, the normal boiling point. Well, what the heck is going on here? It's telling us that this value, the values that we have here, are for the vaporization of liquid carbon disulfide. What's vaporization? Vaporization is going from a liquid to a gas. And so that's what's happening here. We're taking carbon disulfide in the liquid phase and we're converting it into carbon disulfide in the gaseous phase. Now, besides the standard enthalpy change, which we're just going to calculate using these values, the standard entropy change, which we're just going to calculate using these values, it's asking us to calculate the normal boiling point, okay? And before we go in and try to solve for the normal boiling point, it asks us to define normal boiling point and normal melting point, right? It might be a knee-jerk reaction to say, well, normal boiling point is the boiling point at, or is the temperature at which, the substance gets converted from a liquid to a gas, okay? You could just say, okay, well, it's when I take my carbon disulfide in the liquid phase and it gets converted to carbon disulfide in the gaseous phase. That's true, but what's happening when we have a phase change is that the phase change, the vaporization occurs when the liquid and vapor are in equilibrium, okay? Similarly, what's a melting point? A melting point is when we take carbon disulfide, let's say we have it in the solid phase, and we were to melt it, we convert it to a liquid. So similarly, the melting point is when solid and liquid are in equilibrium with one another, okay? That's when they're in equilibrium with one another. Well, we're going to talk more about this in a second, this whole idea of normal boiling point, because I'm going to use it as kind of a segue into the section on free energy change and equilibrium. But I just want to solve for the heat of the standard enthalpy change and the standard entropy change first. So let's do the enthalpy change first. Again, we use the same formula that we used last time. So the delta H for this reaction is going to be equal to the standard heat of formation of the product, carbon disulfide in the gaseous phase, which is given to us right here, 117.4 kilojoules per mole, subtract the heat of formation of carbon disulfide in the liquid phase, 89.70 kilojoules per mole, and all we have to do is punch that into our calculator, and we get our delta H naught of reaction as being 27.7 kilojoules per mole. Well, let's do the same thing for our standard entropy change. Not much of a stretch here. We have the delta S naught for our reaction is going to be equal to 237.7 joules per mole Kelvin. Again, I got that from right here. Subtract the standard entropy for carbon disulfide in the liquid phase, the reactant, or the starting material, 151.3 joules per mole Kelvin. And when I punch that into my calculator, I get that the change in standard entropy in this reaction is equal to 86.4 joules per mole Kelvin. Now notice here again that the units are kilojoules per mole, and the units here are joules per mole Kelvin. I'm going to convert this one to kilojoules per mole Kelvin, and I'm going to show you why in a second. Okay, but I'm just going to divide it by 1,000. So when I divide this by 1,000, I get 8.64 times 10 to the negative 2 kilojoules per mole Kelvin. Now, this is my segue into free energy and equilibrium, right? Because when I do the vaporization, right, this process right here, this is boiling, right? This is boiling the carbon disulfide in the liquid phase, right? We're converting it into a gas. We just calculated the delta H, the standard enthalpy change, and the delta S, the standard entropy change for this process, the boiling process. Now here's something new. We have delta H as being equal to delta H minus T delta S. Well, when this process, and we could go ahead and calculate the delta G, okay? When this process is in equilibrium, the process of going from the liquid to the gas, which is what boiling is, or vaporization, when this process is in equilibrium, delta G is going to be equal to 0. Okay? So again, when these processes are in equilibrium, when the vaporization process is occurring, delta G is equal to 0. So then we can say 0 is equal to delta H minus T delta S. and we can solve this for T. Then we can simply say T is equal to delta H over delta S. So that's going to give us the temperature at which these are in equilibrium, right? That tells us the temperature at which the vaporization or the boiling occurs. Watch. Let's plug in some numbers here. We've got 27.7 kilojoules per mole divided by 8.64 times 10 to the negative 2 kilojoules per mole Kelvin. Look at this. Kilojoules cancel, as do moles, and I end up with Kelvin as being my unit that's left over. And I end up with 321 Kelvin. And so that tells us the normal boiling point. Now, if you're not 100% all the way with me on this concept of the boiling point is when the vapor and the liquid are in equilibrium, and during the equilibrium or at equilibrium, the standard free energy is going to be equal to 0. Okay, the free energy was equal to 0. We're going to talk more about that in a few minutes. Okay, we're going to talk about that in a little bit more detail, but I wanted to kind of put the bug in your ear before we do that. I want to solve another problem, which is kind of an interesting problem. In fact, when I put this slide presentation together for this class, I almost considered skipping this problem. I was like, oh, I'll just leave it out. Then I looked at it more and more, and I thought, you know what? This is second semester general chemistry. Everybody who's hearing the sound of my voice has passed general chemistry 1. And so I thought that this is, if you think about it that way, this is actually kind of an interesting problem. Let's see what I mean. It says, would the formation of water from its elements be more spontaneous at a high temperature or at a low temperature? Explain by determining the sign of delta G, delta H, and delta S for this process. Do you remember last class, we looked at all of the scenarios? Right, we looked at the scenario when delta H is positive, delta S is negative. Delta H is negative, delta S is positive. Then we looked at the two scenarios where both delta H and delta S were positive, or they were both negative, right? Remember, we spent quite a bit of time on that, and then we solved the problem where we ended up looking at all of the scenarios. Okay, well, this is kind of in the same vein as that. In fact, it's very much in the same vein, but you have to use a little bit of your chemical knowledge here. It says the formation of water from its elements. Well, what's the formation of water from its elements? Could you write it in an equation that represents the formation of water? Everybody knows what water is. All right, let's say we had water in the liquid phase. What elements is water made from? Water is made from hydrogen and oxygen. Well, to make a water molecule, I need 2 hydrogen atoms. What's hydrogen in its standard state? Hydrogen in its standard state is just H2. So that means I have H2 gas, right? What's the standard state of oxygen? It's O2. Now, if I had O2 gas and I combined it with H2 gas, I only need 1 atom of oxygen. So I'm going to multiply that by a stoichiometric coefficient of 1/2. So this equation that I've just drawn or written out here represents the formation of water from its elements. Give me a thumbs up if you follow me on that, or let me know if you have a question about that. I'm just showing you take the elements that water is made from, you add them together, and you form water. Okay, thanks, Joey. Good. Okay. Now, I have another question for you. Okay? Really think about this one. And you might have to go back a couple of slides, but we talked about this in the first class, I believe, that we did on this chapter. This reaction, would this reaction here, okay, if I take hydrogen and I combine it with oxygen to make water, is this an endothermic reaction or an exothermic reaction? Does this reaction consume heat or release heat? When you take hydrogen and you combine it with oxygen and you make water. Am I generating heat or absorbing heat? What do you think based on your intuition, based on your knowledge of chemistry at this point? Does anybody have an idea? Does that reaction release heat or consume heat? What do you think? The Hindenburg was filled with hydrogen. There's oxygen in the air. Okay? What happened when they combined? Did they absorb heat from the atmosphere? They released a ton of heat. Okay? This reaction represents the combustion of hydrogen. Okay, that's a burning reaction. Has anybody ever seen somebody blow up a hydrogen balloon in their face before blow it up? When I was a undergraduate student, we had a young professor who brought in one of those giant balloons from Kmart and filled it up with hydrogen, and he lit it on and he blew it up in the class, in the biggest lecture hall in the entire university. He called it the Hindenburg. It made the windows rattle. It put a burn mark on the ceiling, and some people left the classroom crying. Keep in mind, this was the 90s. You could do that kind of thing because nobody had a cell phone to capture it. But hopefully by now, and I don't mean to sound like a meanie, you would know that the combustion of hydrogen is a very exothermic reaction. This reaction is going to release a ton of heat. Okay, a pile of heat. Remember the story I told you about the guys from my class trying to burn hydrogen? They weren't trying to burn it because they thought it was going to absorb heat. They were burning it because they thought they were going to make a big explosion. Okay, it releases a lot of heat. If this reaction releases heat, what would the delta H be? Would delta H be positive or negative? If the reaction releases heat, what's delta H? This is the kind of thing that we need to know, and we need to know it pretty well for the final exam. Yeah, it's going to be negative. This is an exothermic reaction. It's going to be negative, right? This is exothermic. Big time exothermic. Okay? Well, what about delta S? What about delta S for this reaction? I'm taking some gases, one molecule of a gas, another half a molecule or 1 mole of a gas combined with half a mole of another gas, and I'm making one new molecule, and it's a liquid. Would the delta S be positive or negative for this reaction? Am I getting an increase or decrease in entropy based off of your intuition? Yeah, big time. It's definitely a decrease, right? So that means the delta S is also negative, right? We have a decrease in entropy. We've got more particles in gas phase, right? And then over here we have no particles in the gas phase. Even if, and you're like, well, in your last slide it said it was a gas, Mr. Dion. Even if it was, it wouldn't matter. You're going from more particles to less particles. So the delta S is going to decrease. Okay, let's do the exercise that we did last class. Delta G is equal to delta H minus T delta S. So that means that delta G is going to be equal to a negative number, subtract, T is always positive, right? A positive number times a negative number, which means you've got a negative number, subtract a negative number. So it's like you're adding this term to it. So what does that mean? If you want delta G to be spontaneous, okay, more spontaneous is a more negative delta G, right? Is this reaction going to be more negative, more spontaneous at a high temperature or a low temperature? This is what we covered last class. Would it be more spontaneous? Would the delta G be low temperature? Exactly. It's at a low temperature, right? If you don't follow me, look. Think about it. If you want this number to be negative, that's the holy grail. The more negative this number, the more spontaneous it is. Okay, you're taking a negative number and you're subtracting a positive times a negative. Okay, so you want this term to be as small as possible. Smaller will give or provide a more negative delta G, right? If you're subtracting something that's overall negative, when you take a positive and you multiply it by a negative, what do you get? A negative. Okay, so this is saying, again, it's like a negative subtract a negative. right? So you want this number to be as small as possible. The bigger this number gets, then this is going to become less and less negative, right? If you take, look, if you take -2 and you subtract -1, what do you get? You still get -1. If you take -2 and you subtract -5, what do you get? You get +3, right? So if you want a negative number, this has got to be small. That means the t's got to be low. It's got to be a small number. Give me a thumbs up if that makes some sense. Okay, the t's got to be low. So you want to have a low temperature. So the correct answer is the lower temperature is going to be more spontaneous. So we'll put here more spontaneous at lower temperature. Okay? All right. There you go. Well, I hope you guys understand that problem, because I feel like that's a problem that my students should be able to figure out. It's kind of scaring me a little bit that you didn't know this is an exothermic reaction, the combustion of hydrogen and oxygen, because we've looked at that reaction quite a few times, and you would have seen it in General Chemistry 1 as well. But anyhow, I digress. Let's move on and let's try another problem. Let's see, another problem. Yeah, let's try one more problem, and then we'll talk about free energy and equilibrium. This is another good one. Yeah, it says, consider the water-gas reaction, which has been suggested as one way to get gaseous fuel from coal. So you just take carbon, so solid carbon, and you combine it with water, and you end up getting carbon monoxide and hydrogen. Anyhow, there we go. So let's see like that. It asks you, is this reaction spontaneous at 25 degrees Celsius in standard state conditions? Well, we've been given the delta G of formation for water and for the carbon monoxide, and the delta G of formation for hydrogen and carbon in the solid phase, right? The delta G of formation for both of these would be 0 because they're in their standard state. And so if we want to calculate the delta G of the reaction, okay, at standard state, it's going to be negative 137 kilojoules per mole, right? The product, carbon monoxide, subtract the standard free energy of the water in the gaseous phase, which is negative 228 kilojoules per mole, like that. And we get the delta G naught of the reaction is equal to, I wrote it down here, 91 kilojoules per mole. Okay, so my question is this reaction spontaneous? Yes or no? No, it is not spontaneous. No, because delta G, when delta G is negative, then your reaction is spontaneous. Delta G is positive, then your reaction is non-spontaneous, right? Because remember, the delta G was equal to negative T multiplied by delta S of the universe. Okay, we looked at that during the last class. Okay, so in B, it says, determine the temperature in which this reaction will become spontaneous under standard state conditions. Okay, at what temperature will this become spontaneous under standard state conditions? Well, as I told you in question number 8, since this reaction in this direction is non-spontaneous, I told you that when delta G is 0, that's when the reaction will be at equilibrium, right? This is when the reaction will be exactly at equilibrium, is when delta G is equal to 0. So that means if I solve and I say my delta G is equal to delta H minus T delta S, if I put in 0 here, I get 0 is equal to delta H minus T delta S. That means that T delta S is equal to delta H. T is equal to delta H minus delta S. that means I can find the temperature at where this reaction becomes spontaneous, right? Because if the delta G is positive, that means it's non-spontaneous. That means it's going to be favored in the reverse direction, right? It's not spontaneous the way it's written. But again, when delta G is equal to 0, that's when I'm at equilibrium. And that's the temperature at which the reaction is going to start to become spontaneous. So I can calculate my delta H because I've been given all of these heat of formations, okay, right here in this table. I can go ahead and calculate my delta H. That's no big deal. But then where am I going to get my delta S? Well, hold on. If I have the delta H at this temperature, and if I have the delta G, then I can calculate the delta S, can't I? Let me show you what I mean. Okay, first we're going to go ahead and we're going to calculate the delta H. Okay, so I'm just going to kind of do this as an aside. The delta H of the reaction is going to be equal to negative 110 kilojoules per mole, subtract negative 242 kilojoules per mole. I end up with a delta H, which is positive 132 kilojoules per mole. So now I've got my Can you guys see my PowerPoint again, or my PDF? All right, cool, good, thanks. So now I've got my delta H of my reaction. I've got my delta G of my reaction. Why can't I take this formula and rearrange it and solve for delta S? Okay, and when I do that, I get that delta S is equal to delta H minus delta G over T. Okay, now I can solve for the delta S naught of my reaction. So delta S naught for my reaction, okay, is going to be equal to my delta H, which is 132 kilojoules per mole, subtract 91 kilojoules per mole, divided by 298 Kelvin. And I get that my delta S for my reaction is equal to 0. Let me double check this. I'll get my calculator. And you can double check me on this. Make sure I'm 100% right here. 91 divided by 298. Yeah, you end up with 0.138. In fact, there should only be two sig figs, shouldn't there be? Oops. 0.14 kilojoules per mole Kelvin, like that. So that's the same thing as 140 or 1.40 or 1.4 times 10 to the 2, whatever you want to call it. But there should only be two sig figs. Joules. No, hold on. Times 10 to the 2. Go. Joules per mole Kelvin. Like that. Anyhow, there we go. So now we have figured out our entropy, or delta S for our reaction, and we have our delta H for our reaction. And again, I told you that since this delta G, so if you're not following me 100%, I want to be sure that you understand this before I move on, okay? I know I like to harp on some things more than others, but this is really important, you guys. So follow with me carefully. If you're like, what the heck is he doing? Watch. All you did was take these delta G values that were given to you. And the first part was really easy, okay? I don't like to use the word easy in chemistry class, but the first part was very quick. All we did was evaluate the delta G for the reaction, and the delta G was positive. What that means when the delta G is positive is that the reaction is non-spontaneous. It means it's non-spontaneous in the way that it's written. The way that it's written is like this going forward, from carbon plus water, giving you carbon monoxide plus hydrogen. So it means that it's non-spontaneous in that direction, but it's actually spontaneous in this direction. Okay? That's what the delta G means. And what I'm telling you as your instructor is I'm saying, When the forward and the reverse reaction are in equilibrium, when they're exactly at equilibrium with each other, that's when the delta G of the reaction is going to be equal to 0. There's no free energy change at equilibrium. Okay? So equilibrium, that point is going to be where the reaction ceases to be non-spontaneous and starts to be spontaneous, right? It's that equilibrium point. So at that temperature, that's the temperature where it starts to become spontaneous. So all I had to do was set my delta G as being 0, and now I can solve for that temperature. It's something similar to what we did in question number 8 a couple of questions ago. So with that in mind, let's plug in some numbers. I'm going to need some more room over here, so I gave myself some extra room. So we have our T as being equal to delta H over delta S. And again, we had to solve for the delta S using both of these values. We have our delta H as being 132 kilojoules per mole divided by 0.14 kilojoules per mole Kelvin, and then we end up with a temperature which is 940 Kelvin. I actually carried an extra sig fig. I don't know why, but anyhow, it's neither here nor there. It's 942 Kelvin. So that's the temperature at where it starts to become spontaneous. And so you could say at a temperature greater than 942 Kelvin, the reaction is going to become spontaneous. Give me a thumbs up if you just follow me on the concept, because we're going to talk about more about equilibria in a few minutes. But just wanted to kind of go over a couple of examples with you before we really get into the nitty gritty. All right, cool. And especially my students, and it's probably all of you, all of my students who read the textbook before coming to class, you would have seen this in the textbook, obviously. It's a big part of the chapter. But I wanted to take a look at it in a couple of problems before we get into it in more detail. Anyhow, to end this question, the last part just says, what other factors would have to be considered to decide whether this reaction is feasible? Look, I just kind of put this in here as a discussion point with my students. I don't know if I'd ask this question in this way on an exam. I just want to make sure that you're always thinking, that you understand what's going on here. Now, we've figured out what temperature the reaction starts to become spontaneous, right? Greater than 942 Kelvin, it's going to be a spontaneous reaction. Okay, great. Yeah. You're like, no problem, Mr. Dion. I can calculate a delta G. I can calculate a delta H. I can do all those things. Well, what did we talk about at the first day that we discussed thermodynamics? The first day, I said, don't confuse spontaneous with what? Does anybody remember? I kind of harped on it for a little bit. I said, don't confuse spontaneous reactions with being what kind of, yeah, thanks, Violet. You're 100% correct. Okay. All I wanted to do was to kind of bring in, you're all right. Some people are saying fast. Katie says instant. Yeah, it's another way of saying, don't just assume it's fast, right? And I wanted to bring that topic up again. I know I talked a lot about it in the first class, but there's a good reason for that. Okay, it's because I didn't want my students to start thinking, okay, well, it's spontaneous. Yeah, it must be a really quick reaction, right? We don't know anything about whether this reaction is fast or not. So the answer to C, why don't we just say rate? Okay. We have no idea about how long this reaction is going to take. You can just write that in and we'll leave it like that. Okay, cool. That makes me really happy that you guys were able to answer that question so quickly. And again, question number 10 and question number 8, which I put ahead of the equilibrium part on purpose. I wanted to bring in this concept with you that when something is at equilibrium, the free energy is going to be equal to 0. I wanted to bring that into our discussion before we got to this part here, which deals with free energy and equilibrium. Okay, so this is section 16.4 in our book. I probably should have put that in here as section 16.4, where we tie in the concepts of free energy and equilibrium. Remember equilibrium? That was chapter 13, 14, and 15. We spent a lot of time talking about equilibria. And so now we're going to tie it into this chapter, into our thermodynamics. So look, Just about everything that we've talked to up until this point is dealt with standard free energy change, right? It meant that everything was at 1 atmosphere or 1 bar of pressure. Solutions had a 1 molar concentration, right? We even learned how to calculate standard free energy change at different temperatures, right? Because we said, okay, well, delta H and delta S, their dependence on temperature is really small. And so even if we have, we want to calculate delta G at a temperature that's not 298, we just use our good old 298 value for delta H. We plug in the new temperature. We use our good old 298 value for the delta S, no problem. And we can calculate delta G, when we have our compounds in their standard state, or our reactants and products in their standard state. Well, what if I'm in non-standard conditions? What if my reactants aren't exactly 1 molar concentrations and 1 bar pressures? Okay, because that's a very specific scenario, right? As soon as the reaction starts, everything's not going to be in its standard state. Well, there is a general equation that enables you to calculate the free energy change under non-standard conditions. And here is that equation. You need to know this equation. It's delta G. Notice there's no not up here, so that means it's non-standard conditions. Okay, so no not here means non-standard. Okay, equals the change in free energy under standard conditions plus a kind of tuning factor. Okay, which is just R, which is shown here, times the temperature in Kelvin, times the ln of the Q. You guys remember Q, reaction quotient? I know you do, because you worked them out for me hundreds of times, it seemed like, when we were doing those 3 chapters, chapters 13, 14, and 15. I remember you guys were so fast at calculating those kind of Q's and K's. So you're going to borrow those concepts. Okay, so it's basically take the standard free energy change and then you add this kind of tuning factor to it. Okay, so temperature again in Kelvin, R is 0.008314 kilojoules per mole Kelvin. You could also put that in joules per mole Kelvin, which would be 8.314 joules per mole Kelvin. And we'll probably use it each way, depending on what our delta G is. We probably use it both ways. Probably use it this way more, since delta G is usually in kilojoules per mole. But anyhow, and then reaction quotient, everybody here, like Violet says, lots of Q and lots of K. I know you guys spent so much time working on that my students are usually really good at it at this point in the class. Okay, so here's where we tie in what I went over with you guys in questions 8 and 10 in this lecture. So the relationship between Q and K, remember K and Q? Do you remember the significance of K and Q, when they're equal to one another? Right, it's when everything's at equilibrium, right? So the relationship between K and Q is based off of this. When Q is equal to K, so when you can change this to a K, that's when delta G of the reaction is equal to 0. So what would happen if we plugged in a 0 here when we plugged in a K here? You get this formula, which we can solve for the standard free energy change of the reaction. So that means that standard free energy change of the reaction is going to be equal to the negative times R times T times the natural logarithm of K. Now you might be wondering, well, man, when we did equilibrium, we spent so much time solving for K. Would we ever use this formula to solve for K? Oh, I'm glad you asked, because the answer is yeah, absolutely. Okay, absolutely we will, right? We have this formula, or we can rearrange it to solve for K. We would start with, say ln of K is equal to negative delta G naught over RT. And then you would just take the anti-log of that, right? And you get that K is equal to E to the power of negative delta G naught over RT. Now, if you're wondering about which K, Mr. Dion, which K am I talking about? Because we learned about a lot of Ks. You learned about all these Ks in chapters 13, 14, 15. Let me prove it to you. Kc for concentration, Kp for pressure, Ka for an acid, Kb for a base, Kw was the autoionization of water, Ksp for solubility, Kf for the formation of a coordination complex, and Kd for the dissociation of that coordination complex. So you're like, yeah, I guess I did look at a lot of Ks. Well, the answer is you can use any one of those Ks. Doesn't matter. Okay, any one of those Ks can be used in this equation. And now what we've got is we've got a beautiful way to tie in standard free energy change, okay, to the extent of our reaction. Works really well. All right. With that in mind, I want to try a problem from the book where we're going to use this formula, okay? Delta G is equal to delta G naught plus RT ln Q. Let me be honest with you guys. When I was a student, one mistake I made on an exam, and I made it the hard way, and kind of, I probably made it, again. I'm not perfect, that's for damn sure. This is the best conclusion we can arrive at, But I remember, I had done a lot of practice problems where I had used this equation over and over and over. I was doing all kinds of problems where I was solving for delta G naught. And then I went in and I threw in a negative sign in here instead of a positive sign. Okay. I learned my lesson the hard way. So in this equation, it's a plus, but then when you're solving for delta G naught, it's a negative sign in front of the RT. Anyhow, it's just something I did once in my life. I never forgot it. I also got a Lewis structure wrong one time in an exam, and I never forgot that for the rest of my life. Still kind of pissed off about it. All right, anyhow, let's see. That was, over 20 years ago. All right, so let's take a look at a problem where we would apply this equation. So delta G is equal to the standard free energy change plus RT ln of Q. So here's the question. It says, what's the free energy change? So that means we're looking for delta G, not the standard free energy change. What's the free energy change for this process shown here under the specified conditions? So we have 2 moles of ammonia decomposing to give you 3 moles of hydrogen plus a mole of nitrogen, and they've given us the standard free energy change, right? So we've got this, right? We've got the delta G naught. We know what R is, it's a constant. We know the temperature. All we need to do is figure out what Q is. Well, you guys know how to solve for Q. You can probably do it faster than me. All right, you know that Q, and in this case, it's a QP because we're given all the partial pressures. The QP is going to be equal to, oops, I got concentration on the brain. It's going to be equal to the partial pressure of hydrogen cubed multiplied by the partial pressure of nitrogen divided by the partial pressure of ammonia squared. Give me a thumbs up if you remember how to calculate a Q like this. You're like, yeah, I remember that. Okay, thanks, Violet. Good. So let's plug in some numbers. So for the partial pressure of hydrogen, what do we have? 0.250. We cube that. The partial pressure of nitrogen is 12.9 atmospheres. We divide that by partial pressure of ammonia, which is what? 0.870 squared. I didn't work this out, and my calculator's on the floor. If anybody has the Q, could you tell me faster than I can do it? Probably. Times 12.9 divided by 0.87 squared. I get 0.270. Did anybody else get that? No, I made a mistake, didn't I? 0.25 times 12.9 divided by 0.87. I put the wrong value. Thanks, Jamil. I told you I wasn't perfect. You guys are so polite. Should have just unmuted your mic and yelled at me. Okay, there we go. So what's the partial pressure of the nitrogen? There we go, 0.870 and 12.9. Now let me try. 0.25 cubed times 0.7 divided by 12.9. Okay, what did you guys get? I got 8.2 times 10 to the negative 5. Anybody else get that? Actually, you can have 3 sig figs, can't you? So it would be 8.17 times 10 to the negative 5. Anybody else get that? Good. All right, thanks. Appreciate it. Okay, so now let's calculate our delta G. Delta G, and let's put down our units. Let's be very careful here. So we have 33.0 kilojoules per mole plus our R, which we're going to want to have in kilojoules. So that's 8.314 times 10 to the negative 3 kilojoules per mole Kelvin times the temperature. Temperature, 25 degrees Celsius is 298 K. So 298 Kelvin. Okay, looks good so far. So that cancels out. We end up with 33.0 kilojoules per mole plus, did I leave out the ln? Good gravy. Plus times the ln of 8.17 times 10 to the negative 5. There we go. All right, so let's see here. So if you take 8.17 times 10 to the negative 5, take the natural logarithm multiplied by 298 times 8.314 times 10 to the negative 3, you get negative 23.3 kilojoules per mole. And then you get your delta G is equal to 33.0. 33 subtract 23.3. And you end up with 9.7 kilojoules per mole. There we go. All right. Is anybody else trying these with me, or are you guys just waiting for me to calculate everything? All right. Did anybody else get an answer similar to that? It's a question I got from the book, but I didn't check it, and I'm too lazy to look at the book. I'm trying. It's all good. It's all good. Nothing wrong with that. Anyhow, I'm going to assume that's the right answer. I don't have it written in my notes, but move on from there. Okay, 2 people say yes, so it must be good. Does everybody feel confident like they could use this equation? Yeah? Okay, cool. Okay, so let me tell you one thing about that equation. This guy right here, okay? It says, look, this is my introduction to it. It says there is a general equation, and we just tell you the equation. There is a derivation for this equation. It is beyond the scope of our course. It is not covered in our textbook. I mean, if it's not in our textbook, probably not going to ask you about it unless there's some like nuance or something that I really want my students to know. For my students who are really hungry and like need to know the answer to everything and need to know where every formula comes from, there is a derivation for this equation that's in the yellow box, which you could look up, and I would say that you can probably figure it out. Okay, it's based off of entropy. It's based off of the fact that entropy changes slightly. I'm not going to cover it in this class. I debated on putting it in the slides, but the more I thought about it, I'm like, if it's not something that you need to know, there's a lot of things that you know about chemistry that we don't go over in this class. So there's no need of me really adding more things to your plate when we're in a pandemic and the course is already challenging enough, I feel like. But I'm just throwing it out there. If somebody is really, dying to know where this equation comes from, you could probably look it up and figure it out pretty quickly. And that, again, is just for somebody who might be interested. And if you're not, don't worry about it at all. Okay? All right, there we go. I just feel like it's one of those equations that they just kind of throw in your face. You think about, and if you're wondering, like, what do you mean by an equation I throw in your face? Well, if you think about something like the ideal gas law, PV equals nRT, do you remember in Gen Chem 1 how when we learned PV equals nRT? I didn't just give you that formula, right? First, we talked about Boyle's law, then we talked about Charles' law, then we talked about Gay-Lussac's law, then we talked about Avogadro's law, then we put them all together, So I kind of like stuff like that. I like things that tell a story, that kind of explain everything. Anyhow, I'm probably rambling on here. All right. Well, what time is it? 10:28. Oh, we got 3 hours left. Let's try a problem that involves a KSP, that involves another equilibrium problem. Let's read it here. It says, given the standard free energies for the formation of silver chloride and silver chloride are shown here, 77, negative 132, and negative 109 kilojoules per mole, respectively. Calculate the KSP. Oh, this is a good problem. Let's do this one. Okay. So look, they gave us the standard free energies, right? These are just the standard free energies of formation for all of these compounds. So we can figure out the standard free energy for this reaction. You guys remember KSP? Cha, KSP. So you know that when you take a silver ion, right? And this is going into chapter, what was it, 15? Yeah, equilibrium of other reactions. You take silver ions and you mix them with chloride ions. What do you produce? Silver chloride, okay? And this is an equilibrium, sorry. Right? And then you said KSP was equal to what? Concentration of silver plus multiplied by the concentration of chloride. You guys remember that? Give me a thumbs up if you remember that when we talked about KSP. I'm going to assume you do. Okay, cool. Well, if you want to calculate an equilibrium constant, what about this formula? Delta G naught of the reaction is equal to negative RT times the ln of K. That's the second reaction that we looked at, right? And this process is in equilibrium. That's what a K is. KSP is at equilibrium, right? Look, I'm getting overly excited, but I like tying things together. Look, we start with this equation. If we're at equilibrium, the Q is equal to K, the delta G of the reaction is equal to 0, so we can derive this formula. Again, KSP, we're at equilibrium. Okay, well now let's figure out what the delta G for the reaction is, and we can solve for K. I think that's probably the most prudent thing to do. Now, if you're really astute, you probably picked up on that formula really quick, that K was equal to e to the power of negative delta G of the reaction over RT, right? That was just solving for K. But we have R, that's a constant. We have T, okay? It's a standard temperature, which is 298 Kelvin. If we're doing standard free energies, that means the T is equal to 298 Kelvin. So all we need to do is calculate delta G for the reaction. So let's do that. The delta G naught for this reaction is going to be equal to the standard free energy of silver chloride, which is negative, what is it? Did I solve it? It's silver. Where's my silver? I'm getting confused. There we go. 77.1 plus negative 131.2. So I'm just taking the products, the reactants, and I'm going to subtract the let me double check my math here. It's going to be equal to negative 132. Hold on, I think I made a mistake in my math here. Let me grab a pencil. Sorry, I'm having a problem with my computer. Just give me a second. I know what I did wrong. Does anybody see what I did wrong in the KSP? I have my KSP written in reverse. That's why I was getting so confused. Anyhow, let me fix it. I have my KSP expression correct. I had my equation written incorrectly, and all I was doing was focusing on that. Here we go. There we go. Because I was like, well, that doesn't seem right. There we go. Anyhow, now when we calculate the delta G of reaction, we end up with, let's see here, we got 77.1 from the silver ion plus negative 131.2 from the chloride ion, and then we subtract negative 109.8 from the solid silver chloride, and all of that is kilojoules per mole. Then we get the delta G naught of the reaction is equal to 55.7 kilojoules per mole. I had ended up with negative 55.7. I was like, that's not right. All right, let me just, there we go. And now we can plug some numbers into the equation. So we have K is equal to E times negative 55.7 kilojoules per mole divided by 8.314 times 10 to the negative 3 kilojoules per mole Kelvin multiplied by 298 Kelvin because we're at standard temperature. There we go. So we have all of that, which equals, I simplified that to e to the negative 22.46. And of course, I should only have 3 sig figs in my final answer because everything I have has 3 sig figs, or this one has 3 sig figs rather. So I get a K that's equal to 1.76 times 10 to the negative 10, and that is my KSP for the reaction. There we go, like that. Whew. All right, does everybody follow me on that? Does everybody see what I did wrong or why I was getting confused? Is because I wrote this expression in reverse by accident. So again, I had this written out correctly. My KSP was fine, my rationale was fine. But when I was calculating the delta G, I got a negative number, and I knew it shouldn't be a negative number. Anyhow, is anybody with me on that? I don't see anybody. I didn't lose you guys, did I? Are my students still there? Okay, all right, good. I got one person. Yeah, it makes sense. Good, good, good. All right, well, there we go. I think that's enough for today. That covers quite a bit of material. But, you know, really what's the main concept that we looked at today? I'd say, you know, if I only had a minute to talk to you guys, but the main concept for today was what's shown right here. When Q is equal to K, delta G of the reaction is going to be equal to 0. Okay, that was really what I wanted to get covered with you today. And so that means that on, what's today, Monday? That means on Wednesday, we can finish up this chapter for sure. I have a few more practice problems that I have in the slides that I think are really good. And then I'll tell you what, here's what I'm planning. And this is from my lips to your ears. What we'll do next class is we're going to look at the last problems that I have in this slide presentation. So question 11, question 12. We'll talk about coupled reactions just for a second, and that's really it. So that will be the end of the chapter. And then what I want to do on Wednesday is I would like to introduce the concept of electrochemistry to you. Okay? So if I'm going to introduce it, what I mean by that is I'm not going to be going through it super fast or covering any major complicated concepts. But what I would like to do, time permitting, on Wednesday is this. Here's my plan. Number 1, to cover oxidation and reduction with you. Does everybody remember oxidation and reduction? Loses electrons oxidized, gains electrons reduced. What are my students saying? Okay, cool. So I want to review that with you. I know that you learned redox, the concept of redox in General Chemistry 1. I probably taught it to some of you. I know that we went over that with you, but I want to go over it again. Just want to go over it again quickly. And then I would like to look at 1 and maybe 2 things with you on Wednesday. Number 1 is oxidation numbers. I want to make sure that my students understand oxidation numbers really well before we move on to balancing redox equations, because if you remember from General Chemistry 1, we'd spent a lot of time balancing equations, but we never balanced a redox equation. I showed you a couple of them probably, but I never asked you to do it because it's actually a lot more complicated than some of the reaction balancing we did in General Chemistry 1. So again, before coming to class on Wednesday, if you could take a look at oxidation numbers and just review the concept of redox quickly, that will help you a lot. And the reason why oxidation numbers are so important, again, is for you to understand everything else that's happening beyond that. You've got to understand oxidation numbers. So I want to spend some quality time with you on that. Am I not recording right now? It says I'm not recording. Okay.